Hello everyone, this is Mr. Couple, and this is PHYZR number 5, Changing Speeds. This is from the motion unit. It's page number 4. Today's lesson is going to be about getting a speeding ticket. A speeder will be tearing down the highway and get spotted by a police officer who's going to pull over the speeder and give her a ticket. In this lesson, we'll be talking about concepts of uniform motion and accelerated motion, as well as talking about motion graphs. Let's get started. Suppose a car moves on the highway at a constant speed of 40 meters per second. That's 90 miles per hour. And here comes the car. We'll take a picture every 1 second, and that'll be that little ghost image left behind. So each of those images shows us the location of the car, the position of the car, at 1 second intervals. Now this car was traveling at a constant speed of 40 meters per second. So my question for you to think about is, how far does the car travel each second? So my question is, from the tip of this to the next tip, this is 1 second later, what is this distance if the car is traveling at 40 meters per second? If you're having trouble visualizing it, I'm talking about this distance here. So if the car is traveling at 40 meters per second, that means that every second the car travels 40 meters. So from 1 to 2 seconds, the car travels 40 meters because another second has passed. Every second that passes, the car travels 40 meters. And that's what it means when we say the car travels at 40 meters per second. We mean that each second the car travels 40 meters. And since this car was traveling at constant speed, we see that the images taken 1 second apart are evenly spaced out. This signifies constant speed. Now, when an object moves at constant speed along a straight line path, we say that it is in uniform motion. This is a very special case of motion in which a car is traveling at a constant speed and traveling in a straight line path, which means it has constant velocity, that neither the speed nor the direction are changing. And this is called uniform motion. Uniform motion is extremely rare. There's very few objects in nature that move with uniform motion. It's a very special case type of motion, and that's why it's going to be the first one that we're going to be talking about today. To better understand uniform motion, we're going to make a motion graph. The way a motion graph works is you show the position of the object at all time. So we'll be graphing the position versus the time. Time is the horizontal axis, and position is the vertical axis. So what we'll do is we'll look where the car is over here at 0 seconds, and we'll say at 0 seconds the car has traveled 0 meters. And that'll be the first point on our graph. So that shows that at 0 seconds the car was at position 0 meters. We'll continue to do this for all positions for all time. So go to 1 second, and since the car is traveling at 40 meters each second, we know the car has traveled 40 meters at that point. So its position is 40 meters at 1 second. We continue this for 2 seconds. Now the car is at 80 meters. We add that to our graph. And finally at 3 seconds, the car is at 120 meters. So we assume that in between those dots, the car was traveling at constant speed, which means that every incremental time that passed, the car inched ever so further ahead. And so we'll draw a straight line that connects all those dots together to signify that the car was traveling at constant speed. So you can see that as time increases, so too does the position. And we get this nice steady increasing curve. Now the question is, why would we do this? What use is a motion graph? Well, it turns out that it's really easy to calculate the velocity if you have a motion graph, because the velocity is simply the slope of the graph. So if we wanted to calculate the velocity of the car from 0 seconds to 3 seconds, obviously we should get 40 meters per second. So let's check it out. The slope is the rise over the run. So from 0 to 3 seconds, you can see this is the rise of the car. The car has traveled 120 meters. So we'll substitute in for rise. And from 0 to 3 seconds, the car ran a time of 3 seconds. We plugged it in for the run. And so you see that 120 meters divided by 3 seconds gives us 40 meters per second, which was precisely the speed of the car that we set at the very beginning. So you can see graphing a motion graph is very, very, very helpful in terms of understanding the motion. Whenever you see a straight line like this, it represents uniform motion or constant velocity. Notice further that the slope of this graph is positive because the car was traveling east in the positive direction. Uh-oh, there's a police officer on the side of the road at rest. And here comes the speeder, totally caught. So the police officer is at rest and notices the speeder pass by. I want you to explain how the police car can catch up to the speeder. What does the police car need to do? If the police officer did nothing, he would just sit there because he's at rest. So obviously what has to happen is the police officer needs to step on the gas and needs to chase after the speeder. The police car must increase its speed so it can catch up to the speeding car. So not only does the police car need to speed up from rest, but it will also need to go faster than the speeder to catch up to the speeder, because the police car will need to travel a greater distance each second in order to gain distance on the speeder. But what I'm really focusing on here is the fact that the police car will need to change speeds. The speeder was going at uniform motion, constant speed, but the police car is going to need to speed up. Let's take a look at this from a further perspective out. So you can see the speeder is going at constant speed, but now the police car is catching up, speeding up, closing that distance and closing the distance until finally the police car pulls over the speeder. And what I want to do is put some markers on here for distances. And we've already got images of each 2-second interval of these pictures. And so let's graph this. So you can see the speeder starts at 0, 0. And then at 2 seconds, the speeder is at 80 meters. At 4 seconds, 160 meters. And so on all the way up to 400 meters at 10 seconds. So once again, we see a straight line for the motion graph of the speeder. The police car is going to be a little bit different though. If you notice over here, the difference between the two sirens, look at this. The police car has barely moved at all in that first 2 seconds. The police car has barely moved forward at all. So the police car starting at 0, 0 barely moves forward at 2 seconds. At 4 seconds, we're about here, which you can see is almost halfway, almost 40 meters. So almost to 40 meters. At 6 seconds, we're a little bit past 80. See here, a little bit past 80. At 8 seconds, we're getting closer to 240. We're definitely past the halfway point here, which would be 200. So we're a little bit past 200. And at 10 seconds, we're well past 320, but not quite to the halfway point. So we would be here. And what do you notice about the shape? It's not straight. In fact, it's curving. We'll talk a little bit more about what it means when it's curving here. So please remember that this purple line, that's the speeder. The blue line is the police car. Just take a moment to look at the shapes of these two graphs. Notice how they're different. In fact, you should also notice how the police car is gaining on the speeder. Notice here the distance is very short, whereas here the distance between them is very large. So you can see that this is the time where the speeder has passed the police car before the police car has had a chance to catch up to the speeder. And then you can see that gap starts to narrow until the police car finally pulls over the speeder. I'm going to play back the animation of the chase, but I'm going to make the motion graph appear at the same time as the animation is appearing so that they'll appear in sync. So check this out. Remember that the slope of a motion graph is the speed. And this is going to be the key to interpreting this graph and understanding what's going on here. So check this out. This little red line here, this is the slope of the speeder's graph, and that X signifies the location of the speeder. And so watch what happens. As we move forward in time, look what happens to the slope of that line. Nothing happens. The slope stays the same. Why does the slope stay the same? Because the speed of the speeder is the same. Let's do the same for the police car. Notice the police car starts off at rest. There's no slope here. And look what happens as time passes. The slope increases. In fact, at the end here, you can see that the slope of the police car is steeper than the slope of the speeder. And that's because the police car is catching up to the speeder. So what does a curved motion graph indicate? On a motion graph, what does a curved motion graph indicate? Have you figured it out yet? When a motion graph is curved, it means change in speed. So if you see a motion graph that's curving, it means the object is changing speeds. Or you could put this another way and say that a straight line on a motion graph represents a constant speed. So one more time, let's just take a quick look here. So you can see that the police car started off at rest, and it got faster and fastest. As time passes, the slope of that line is getting steeper and steeper and steeper, and that's because the police car was speeding up to catch up to the speeder. This concept of a changing speed in physics is called acceleration, and it's symbolized with a lowercase a. And the definition of acceleration is the rate at which an object's speed is changing. Or to put it another way, it's how quickly the speed is changing. How quickly an object's speed changes. The unit of acceleration is meter per second per second. So you see it's speed per time. Meters per second, there's your speed. Per second, there's your rate. So essentially what acceleration is then is it's the change in velocity that an object experiences over a certain amount of time. So using this definition of the rate of change of speed, we can actually define acceleration as delta v over delta t, or say acceleration is the change in speed over the change in time. So what I want to do now is take this new formula and apply it back to the motion graph that we just showed for the speeder and the police car. And I want to try to calculate the acceleration of each car from the motion graph. Let's watch this animation one more time. I want you to notice right around 5 seconds, that's right about now, the police car starts to close that gap and it finally catches up. You can see that on the graph here. You can see this gap is getting bigger and bigger and bigger, and right about here it's at its maximum distance, and then get closer and closer and closer after that point. We want to calculate the acceleration using our definition of acceleration from 0 seconds to 5 seconds. The reason I chose 5 seconds is because that's where the gap between the two cars is the largest. So let's calculate the acceleration of the speeder. We'll use the definition of acceleration as the change in velocity over the change in time. And if we plug into this formula using the delta as being final minus initial, then we see we have 5 seconds minus 0 seconds for being the change in time. Now remember, the speeder was going at a constant speed of 40 meters per second, which means at 5 seconds, the speeder was going 40 meters per second. And at 0 seconds, the speeder was going 40 meters per second. It had constant speed the entire time. And if we do the math on this, you see we have 40 minus 40 on top, which is going to give us 0. And 0 divided by anything, in this case 5, is going to return 0. That's because the speeder was in uniform motion. There is no acceleration if the velocity is not changing. If an object is going at constant speed in a straight line, uniform motion, the acceleration is 0. We'll do the same for the police car, the same formula, same time interval, but we notice that at 5 seconds, at that point, that's where the speed of the police car matches the speed of the speeder. And that's why the gap there was the largest. Past that point, the police car starts to go faster than the speeder and starts to close that gap. But at 5 seconds, the time that we're looking at here, it had the same speed as the speeder. So the police car had a speed of 40 meters per second. And remember what the speed of the police car was back here at 0? The police car started from rest. And if we do the math here, you see we have 40 divided by 5, which is 8. So the police car was experiencing accelerated motion. Every second that passed, the police car gained 8 meters per second of speed. And that's how the police car was able to catch up to the speeder. And if you think about it, if every second we're gaining 8, that would mean 1 second it's at 8, 2 it's at 16, 3 it's at 24, 4 it's at 32, and finally after 5 seconds it's at 40 meters per second. And now the police car can start to gain and catch up to the speeder. Well, that's it for this PHYZR. This has been Mr. Keppel, and I'll see you in class.